So thank you very much for coming. And the first question is expectation values, or at least how I pose this question. How do we get expectation values to be used in a practical problem? Do we observe them? If not, how are they obtained? So Professor Giffin, would you like to start off?
Sure.
And there's another microphone.
Okay, well, one microphone would probably suffice. The maximum entropy principle is supposed to be motivated by a desideratum of honesty, to take into account that what we actually know about the problem and not presume that we have some hidden additional knowledge that we in fact don't have. That's why we maximize the entropy of a probability distribution. But to get the whole method off the ground, we need a constraint. Because otherwise, if we simply maximize entropy over all probability distributions, we always get up with the same answer. It's the uniform distribution over whatever number of outcomes you have. So you need a constraint, that is to say a subset of the probability distributions over which you actually perform this maximization. And then the question is, how does this constraint set get chosen? And indeed, the most popular method that I've seen in literature is to choose constraint sets which fix the expectation value of some function. And then the question is, what is that value of that expectation function? Now, in James's work, you often see that that expectation value gets borrowed, that value of the expectation value gets borrowed from experimental input. It equates the expectation value with the average that is obtained in some number of experiments. But that leads to various deep problems. An expectation value characterizes a probability distribution, and therefore, if probability distributions are, as James claims, states of knowledge, that is to say, they're in your head, they're not out there in physical reality, the question why observed averages should be put equal to these expectation values is something which, in my view, cries out for an answer. James himself has written about this repeatedly, but I don't think his remarks were very convincing. And in my point of view, I simply don't know of any compelling or even convincing motivation to set these expectation values equal to numbers that you obtained somehow from empirical experience. From all the literature I've seen, there's only one method which I found vaguely appealing, and that is the motivation described by Van Fraasen, who simply describes the constraint as a voluntary decision on the part of the agent in question to constrain his beliefs or his probability distributions to be members of a certain set. And this is not a decision which needs to be motivated by experience. It might be completely just for whatever arbitrary decision this person happens to be making. And if that's the point of view, I know of no fundamental objection against it. The practical objection against it is that it gives you, if you want to use maximum entropy as a practical method, you simply have no clue to choose whatever constraint you're going to apply. You have to make that decision for yourself, and the method simply remains silent about what would be the appropriate choice. And if that's so, then I think the practical usefulness of the method is very much diminished. And I think that would be sufficient for the moment.
Yeah. Next?
Yep.
Well, I'll first address your remarks about agreeing graciously to do this.
Okay.
When someone of your physical presence makes a request, one somehow naturally agrees to it. Not very graciously, but
I can't be physical through email.
it's all right.
If I'm intimidating through email, then that's really impressive.
Yes, sir.
Okay. Well, I wouldn't have quite put the questions this way, so the answers I've got will be a bit different. But let's start in this approach. Maximum entropy, as is commonly understood, and I've got some slides which will vary this, but as commonly understood, it's an assignment mechanism for assigning probability distributions. Clearly, you need constraints on that. Constraints to do with probability distributions are naturally linear in probability. Sum of pi times something I makes sense, whereas sum of p squared doesn't. P is a measure, so it can only be applied linearly. Although you can have nonlinear functions, but they all, as in quantum mechanics, you have to have linear functionals. So how could we apply this to data analysis? I'm started in this game in data analysis. I want to help scientists. That means I've got to use their data. And their data are always a bit fluffy. They are probabilistic. I may have a list of thousands of numbers, different probability weightings. What do I do with them? I cannot take them at face value, because if I did, I would be fitting each datum without considering its error bars, and that would lead me to maximum likelihood, and that is known to be completely hopeless whenever you're trying to deconvolve things. So I have to take into account the error bars. Okay. One thing you might think of is taking the mean plus sigma to minus sigma as a range, and taking the maximum entropy to anywhere in or of the boundary of that range. That sort of makes sense with one constraint, but it certainly doesn't make sense with lots of constraints. If I had lots of constraints and I tried to do this, I would end up maximizing entropy over some sort of hypercube. Lots of different data, giving me linear ranges in different dimensions. That would be a nasty computational problem, and I'm not too bothered with that because I'm an algorithm designer, but it would be a bit unpleasant, not differentiable and so on. And it would also remove an invariance. Because if I have Gaussian errors in 2 dimensions, and I've given them in these rectilinear coordinates, that's quite equivalent to taking them in diagonal coordinates, in which case I would have a cube that was all the other way around. And equivalent problems, these coordinates and these coordinates, should give me single answers. So that invariance means that I cannot take just ranges on the individual data. Okay, what I can do is constrain on the likelihood value. So that is coordinate invariant. The likelihood at any point is the sum of the misfit square, whatever it is. So instead of having maximum likelihood, which is minimum chi squared, I now have a range, typically an ellipsoidal range, of acceptable solutions. Well, that's how our maximum entropy data analysis started in the 70s. Chi squared equals n is the constraint. We maximize entropy over some sort of elliptical domain. But clearly we are losing. That doesn't, because we may have a problem in which the first 100 data are meaningful, they attach to our problem. The next 1,000 data might be just pure noise, not related to the data at all. And I must surely be able to analyze the data that matter and data plus something irrelevant and get the same answers. Because if this other data is irrelevant, it's irrelevant. That shouldn't change my results. And chi-squared equals n would eventually become dominated by this huge potential tail of stuff that's irrelevant, plus or minus its square root n variability, and would eventually destroy what I was trying to do. So chi-squared equals n doesn't work. So then we try to refine it and find out what we call the good degrees of freedom inside chi-squared equals n. That's worked quite nicely, except that it had to be some sort of probabilistic estimation of how many data were good and how many weren't. And we ended up having no escape but to say that the entropy itself had to be probabilistic. Because if the constraints of applying are probabilistic, then the entropy itself has to be probabilistic. And that wasn't working either. So, for data analysis, I don't think we do use expectation values. We can use likelihoods, because that's what Bayes' theorem tells us to do. And we can use priors on what we're looking at, because that's what Bayes' theorem tells us to do. But that's nothing to do with MaxEnt. MaxEnt is to do with assigning measures, altering them. And I'm in sympathy with your colleague that says that ultimately the constraint set has to have some sort of ill-defined subjective characteristics. I think that's the way of the world. It doesn't prevent us doing things. It doesn't prevent us using entropy as a good regularizer. It doesn't prevent us getting very nice pictures that help a lot of scientists. But it does mean that expectation value of data rather missed the point. I hope to put that in pictures later on, but that'll do for now.
Okay, let me sure. I have I must start by saying that I agree with yours. It's a very good description of the problems, the conceptual problems with the method of maximum entropy as evolved after James. I think that's, I only have, yes, 129. I lied to you. Same number that Luca used the other day. So it's here the question. So this is two slides on values and averages. An expected value and a sample average are not the same thing. Did you? They are conceptually very different. Numerically different most of the time, except perhaps in very special situations. In those very special situations, one could use the numerical value of this quantity as an approximation for an expected value there. But otherwise, don't use it. The default is don't do it. That's it. Otherwise, you're going to be in trouble. That's the first one. Second slide. Why would you use an expected value as information? And why would you do that? Well, there is a common answer, and this is the answer that used to be given by James all the time. Maximize entropy subject to an expected value, because this is what we happen to know. This is what's known. This is the honest thing to do. Put whatever you know and proceed from there. This is all right. This is all right. If you happen to know something, use it, impose that your posterior distributions, your distributions are in agreement with that piece of information, and you make the best possible predictions on the basis of that information. That's good. It's fine. The question that arises is whether the best possible predictions are any good at all. They might not be. So here is a second answer. It's a little bit stronger. Maximize the entropy subject to an expected value constraint, because this is what we need to know. If you pick the right constraint, then the chances of getting predictions that not only are the best you can do, but also they are useful, reliable, is much higher. The problem that arises, of course, is you may not know once, for example, doing statistical mechanics, if you are describing thermodynamic equilibrium, you may very well want to use, you need to know, or you will need to impose a constraint on the expected value of the energy. One of the objections that, because otherwise you get wrong results, period, that's it. You need to know this. Now, one of the ways that it used to be formulated was that you need to know the expected value of the energy because this is what we know. Objection. This is not what we know. Nobody ever says, I'm going to maximize subject to a constraint on the energy because I know that the value is 3.2 joules. That's not the way it works. We do not know that. It is what we need to know. So, the result of imposing such constraint is that if you impose a constraint like this, what you get is a probability distribution like that. Problem. This value is unknown. Therefore, that value is unknown. But we do have a family of probability distributions. So how could you possibly determine this value? Well, then you need additional information. The additional information can be obtained either by using a direct measurement, just use a thermometer, or you use Bayesian inference, and here you see that you have a problem in parameter estimation. Go and determine that parameter. The logic of the argument is very different. It's not that we know this value. None of the value is not known. It's that if you want reliable results, this is the kind of constraint that somehow captures objective aspects of the world which we want to put into our inference engine. And then, of course, you still need that additional piece of information. Thank you. No more. Very good. The slides only. Just minimizing this. Sure.
So I'm going to be out of the way for the expert, but I do want to comment on this particular question very quickly. Ariel mentioned this in his talk, and I completely agree with Ariel in the sense that, except in the asymptotic case, clearly expectation value is not a sample average, and you cannot use it. If you do something else, it's illegal. Now, I happen to do probably a lot of illegal things to be able to eat, to feed my family, to do all kinds of things. And so some things are extraordinarily useful, although they are completely illegal, like using a sample average that is Avogadro's number. Not asymptotic, but still very large. The other issue with this that I find is that if one says, and I mentioned this in my talk, if one says that you get this expectation value from, say, thermodynamics, so take statistical mechanics. This is always kind of defaults onto statistical mechanics. You have statistical mechanics, you discover beta through the temperature. There's some, we're assumed it's exactly known how thermodynamics works, and beta comes from the temperature. Okay, so you say you use a thermometer. Great. So I use a thermometer and I make an observation. So right away, I'm connecting, even in the statistical mechanics case, expectation to observation. Then I take many observations and I have an uncertainty. So I can use Bayes in the normal way to maybe pick the mean temperature that I'm measuring or something like that. But in the end, I'm back to using Bayes for that expectation value. Now the problem with that is that when you're using Bayes, you always have to start with something. For instance, if you have a Gaussian, you might want to know sigma. What is your uncertainty? How do you determine your uncertainty? And there are ways to do that. But I find that there's a little bit of a chicken and the egg argument here that is puzzling to me. And what it really comes down to is usefulness, as been mentioned many, many times in many, many talks here. And so that's what really puzzles me is how do we measure usefulness, except in the fact that somebody dies by choosing something that somebody lives by. And maybe that's ultimately the only way to measure usefulness. So that's all I wanted to say. Thank you. I wanted to give the panelists an opportunity to respond to anything that any of the other panelists had to say before moving on to the next question.
Bad idea.
That's the ultimate idea. Please, go ahead. Yep.
Okay, thank you. Well, I have a few responses. First to Ariel, I obviously agree with most of what you said, but in particular with the statistical mechanical case, but I do think it's a little solace because yes, in statistical mechanics we have been using canonical distributions for more than 100 years. We know that these are the right distributions to describe thermal equilibrium, and therefore if you want to employ maximum entropy, you'd better come up with distributions which people liked and loved all along. And yes, in that case, what you need to do is you need to choose a constraint in terms of the expectation of the energy. So that's a case where you can find the appropriate constraint because you already know what you want the answer to be. And if maximum entropy is going to be a more general method, yielding useful results, even in cases where we don't know what the right answers are going to be, we are still a bit in a fog about what constraint would be the appropriate. I also have a question to Professor Skilling, who mentioned that constraints had better be linear because probabilities are measures. I don't quite understand that argument. As far as I'm concerned, there would be no... So linear constraints are obviously very nice and easy to use because we can solve the maximization problem immediately using the Lagrange multipliers. But why would it be inappropriate, for example, to constrain on a standard deviation instead of an expectation? That would not be a linear constraint in probabilities, but it certainly could be useful.
It's integral of x squared p of x dx.
No, minus the expectation value squared and then the square root. It's a
non-linear function of linear functions. That's okay.
Yes, but it's that. What do you mean that doesn't?
You want the.
I know what the expectation value is,
which
but
is linear.
It's not the case that the standard deviation of one probability distribution. Sorry, if I take a linear combination of two probability distributions, then standard deviation is not the average of the standard deviations of the component probability distribution. So it would not be a linear constraint.
It's a function of linear constraints. There's the 0th moment, which is 1. There's the first moment, which is the mean. There's the second moment, which is the variance about 0. And then there's the square root of that minus the first moment squared. And that's a non-linear function, but it is of linear functions. And that's what a constraint.
But in the probability space, it would not be
that
a
is
straight.
Sure.
Line or
yeah.
Okay.
But
Okay. Well, then I understand.
Okay, Jonathan. Anything else you want to, Jonathan? Anything else you want to say? John, it's your mic for a rebuttal if you wish.
I have nothing I wish to rebut.
Okay. Ariel, do you have anything you'd like to add?
I just want to agree with Jos that figuring out what are the relevant constraints is really a difficult problem. And we need more systematic ways to go about doing that. It's not a problem that is just peculiar to the method of maximum entropy. It's a problem that's peculiar to the whole of science. Figuring out that the right thing to focus on when you study superconductivity is the wave function of the Cooper pairs is a major achievement that's only really achieved by trial and error. You try different things. When someone finds the right thing, that's a genius. It's a really difficult thing to do. The only systematic way we have of figuring out what are the relevant constraints for a particular problem is to go to school and learn from people that are going to tell you the answer. And if the problem is a new one, no help there. You need someone to go figure it out. It's very difficult. On the issue of linear constraints, I think that linear constraints are particularly useful and very important, but there is no requirement that they be linear. In fact, most of my work over the last N years has been on really exploiting constraints that are not linear. There are other types of constraints. For example, what Francesco was telling us today about entropic priors, those are not linear constraints. They're constraints on the functional form of probability distributions, or we could have geometric constraints. There are all sorts of other, any constraint will do. Any constraint will do.
As long as it's convex. As long as it's convex.
Not even. Not even. When a constraint is convex, it gives us a single probability distribution that's selected. If a constraint is not convex, it may give 2 or 3 or whatever. And that's fine. The method is honest enough to tell us that with that piece of information, there are several possibilities. That's all right. I'm willing to do that. Yeah.
Okay, thank you for the panel. Let's try to move along here, please. I know slides are still coming. So
129.
The next question I proposed was, is MaxEnt and Bayes compatible on any level? If so, how? If not, why not? What about priors? And when I put priors in there, I was thinking specifically that in James' work, when he takes Shannon entropy and the continuum, and he has to add the measure for invariance, and he says that this is information you get a priori, but it's not a prior. So I understand, I think what he means is that it's not a Bayesian prior, certainly it's prior information, so that's why I put priors up there. But John, can you lead us off on that question?
Yes, but I'm going to do it with the slides. Full screen, where's that?
Click play, John, top left-hand corner.
Upper right-hand corner, play right below that.
Oh, yeah. Okay. I'm going to disagree on this linear thing. I think linearity is fundamental. Kevin and I have been looking at the foundations of all this in as much detail as we really can. And we find that probability is to do with measures. Probability of measures is a measure. There's only one calculus for dealing with measures, and it's the sum rule. And the reason for that is... No, I had
John, it's
I had
on
my
the
own
desk.
pointer. Oh, there it is, on the desk. Thank you. The reason for that is that stuff can be combined as a conjunction operator. If I have stuff, then this is more stuff. And there's an ordering axiom as well, that if this has got more stuff than this, then that remains true, even if I add something else. And those two axioms themselves force the sum rule and I want also to be able to deal with independent systems. So if I have two systems, something to do with the Tokyo Stock Exchange over here, and something to do with the temperature of Alpha Centauri over here, I want to be able to analyze them both together and not interfering with each other. Those symmetries themselves, alone, with no side conditions of continuity or differentiability or anything like that, I believe force us to use measures. If then we want some sort of distance or variation or potential, to be more abstract, or divergence, call it what you will, we're going from one measure to another, there's only this one possibility. For some reason, its importance has not been generally recognized to such an extent that it hasn't even really got a proper name, which is a bit of a disgrace, because it's totally fundamental. It's the only selection criterion compatible with the symmetries. It reduces the Kullback-Leibler for probabilities, and if all the Q's, all the weights of the states are the same, then you pop back to Shannon. And because these are all the way around, we've got these two things. We've got information, which is the Kullback-Leibler, Shannon, which just starts from absolute zero with equal weighted things. So it's physics up here with MaxEnt, and there's inference over here, which is really minimum information. There's a certain amount of confusion can arise there. Now, what we have done in the data analysis, and what I want to think about is actually being helpful to scientists, which means doing data analysis. What we did was find pictures, spectra, whatever, which minimize the information or maximize the entropy, whichever way you want to put it, of F, the thing we're interested in, relative to something we didn't know where it was. This is trying to reconstruct a picture from data, and at first you have no idea where anything might be, so you just say flat, and then we try to do something better. Now this was regularization. This is not Bayesian. This is trying to find a single best result for the user. Someone wants a nice picture to give to the sponsors. This is it. We kludged it up with some sort of Laplace approximation, thinking about entropic priors, but that was cosmetic and turned out not to be proper science.
So F is not a probability distribution.
It could be a probability distribution.
Not the problem you were describing right now, right?
No, I'm coming to this. The general point is that the formula, the P log P formula we're talking about, is actually to do with measures which do not have to add up to 1. Applying it to probabilities is only a special case. It's a special case that 99% of people think about, but it's only a special case. And for general imagery construction, we want the amplitude as well as the shape. Now, if I do have a measure, I can, of course, normalize it. And of course, I can think of this thing as radiating photons at me, and finding out where the next photon would come from would be the shape of this thing as a probability distribution. But we've been more general than that. This is the picture of what we have actually been doing. MaxEnt is a way of getting you from something you don't know to a single result. Bayes gets us from some prior of what curves might have been, and then produces some tighter family, which we call the posterior. These are different problems. They're different things. There can't be any deep incompatibility, because they both rely on the same symmetries that underlie measure theory. So they can't be inconsistent, but they are different things. What matters to both is that we have some sort of starting place that's assigned outside this system. All this starts with this formula. You have to start with a Q before you could get a P. There is no free lunch in this world. You must have some idea of where you start before you can go anywhere else. Now you can back off and say, oh, I don't know what Q is. I'll give it some probability distribution. Okay, but then I'm going to assign that probability distribution, whatever parameters go into it. I can say, oh, I don't want to do that. I'll have prob of Q, and I can sort of disappear up by you know where. So that's, I think, an essential part of the problem. Yeah, that'll do.
Area?
Whenever I talk about entropy, I only mean it to refer to probability distributions, because I think of entropy as a framework, entropic framework, something that is designed for a purpose. John had a very clear purpose when he designed his entropy based on certain symmetry properties. I may have a slightly different purpose. Where is technical? So this is. So, are Bayesian and entropic methods compatible? Yes. Let's be clear about the goal. The goal I am interested in is to update probabilities when new information becomes available. It's a problem of learning. So just to set the stage clear for what's coming, let me start by saying I have decided on a particular set of propositions. I try to write here to lattice, to say that in some respect this is very, very compatible with what Kevin Knuth and John Skilling and Royale have been around with. So here we have a set of propositions, and on this set of propositions I will sprinkle this with probabilities, and the probabilities are going to be constrained to be consistent. They have to satisfy sum and product rules. In particular, if I am interested in Bayesian updating, then the propositions that I'm interested here are going to involve not just the parameters that I am interested in determining, but also the values, the possible values of the data. I have not yet collected data, so I'm talking about probability distributions of X and of theta. The space here is the joint space of X's and thetas, and of course they have to satisfy a product rule. Very good. Now I acquire some information. The information is typically going to be in the form of data, and this allows me to update to the same set of propositions now being sprinkled with a new set of probabilities. These probabilities also have to be consistent. They have to satisfy sum and product rules. The little distinction that I want to draw here now, it's a matter of language. And language is supposed to be useful or not, and if you find it useful, please use it. If you don't find it useful, just pay attention for 5 seconds and then forget it, okay? The point I would like to raise is that given the product rule, this product rule, which is a matter of consistency, I can immediately write a Bayes theorem here. Given this product rule, I can immediately write a Bayes theorem there. So there is a Bayes theorem, there is a Bayes theorem. That's correct. It's a matter of consistency. Now, the problem that I am interested in is the problem of updating from priors to posteriors. So I'm going to introduce a new name now for this rule that allows me to go from Q's to P's. This is exactly the kind of stuff that Alexis Toda was discussing today. That's why I like his work, because it's sort of very consistent with the kind of language that I would use. Bayes' theorem operates at this horizontal level. It's a matter of consistency here. Bayes' theorem operates at this level. It's horizontal there. Bayes' rule is a rule that allows me to connect Q's to P's. It's a different animal. Two are going to end up being very intimately connected, but conceptually they're very different. So how do we do this updating? Well, it requires a fair amount of justification, but the appropriate entropy to maximize is the entropy in the joint space. To my knowledge, the first person who very forcefully advertised that this was the right way to think about Bayes' theorem when one is trying Bayes updating, when one is trying to use entropy arguments was Carlos Rodriguez. This is the updating law. We want to go from priors to posteriors. What is the prior probability distribution we want to use there? Well, it's that. This is typically what we would call the Bayesian prior for theta, and this is what we would call the likelihood function. From this point of view, both are prior information. They're the prior distribution on the joint space. And very good, those are the priors. How about the constraint that we're going to impose now? We acquire information, that's a constraint. The constraint is something that's going to tell us what this guy here is, and this is going to be constrained by the data. If the data is very precisely well known, then we would like to say that the marginal of this probability distribution is supposed to be now very well defined at the value of the data. So this is our constraint. Now it's a matter of mathematics. Oh, by the way, and if you do not know this very, very precisely, it's perfectly okay to put some other probability distribution there and say that maybe your actual data was a little bit uncertain. You can do that. It can be generalized in a number of ways. Very good. So how do you proceed to do it? The result when you do that is that the posterior, which can always be written in this way, Bayes' theorem, turns out to be, and this is the updating, turns out to be that, once you maximize the entropy. This piece is the constraint that one imposed, and that part, the fact that the posterior conditional matches the prior conditional here, that was the result of maximizing entropy. The net result, the new marginal for theta, phi, the new marginal for theta, is, well, it's a delta function to the integral, blah, blah, blah. It's the prior conditional probability, which, of course, just using consistency, we can write it in terms of Bayes' theorem. So, there are two things here. There is Bayes' rule, and updating takes you from Q's prior conditional probability to the new posterior. This is Bayes' rule. That one is Bayes' theorem. This part has nothing to do with entropy. Completely independent of entropy. Entropy never entered in writing this equality here. So when you're inclined to say that maximum entropy, MaxEnt, has nothing to do with Bayes' theorem, yeah, I agree. However, as far as the updating goes, going from Q's to P's requires a little bit more than here consistency, and that's where entropic arguments are. So this shows that entropic arguments and Bayesian arguments are completely compatible. You have to be a little bit picky. Yeah, you have to be nasty and be picky about the words you use. And once you know how to use them, you can forget about them and proceed.
Well, I haven't prepared any nice slides for this question, but my answer to the question about the compatibility of Bayes and maximum entropy methods is, in a sense, yes and no. And let me first recapitulate what my co-panelists have already said with so many words. One has to be careful here. Maximum entropy methods, in my mind, fall apart in two separate principles. The original maximum entropy principle, as Professor Skilling has mentioned, is a method for assigning probabilities. This should be distinguished from a method in which one uses the maximization of the relative entropy, or the Kullback-Leibniz entropy, which has by many people been proposed as a method for updating probabilities. Bayes, on the other hand, is also a name which means different things for different people. On the one hand, there are many people who call themselves Bayesians because they favor a subjective interpretation of probability and associate that with the name of Bayes. There is Bayes' theorem, which, as Ariel has pointed out, is just a simple theorem of probability theory and no particular position with which you can agree or disagree on. There's Bayes' rule, or Bayes updating, which is a rule for how to change your probability distributions in the light of new data. And that's something on which people can agree or disagree on. And then finally, there's also the way that Bayes himself used his rule, his updating rule, in a statistical problem, and in which he allowed himself to attach probabilities to unknown probabilities. And that's also typical for what some people associate with the name Bayesianism, although there are also many Bayesians who deny that the legitimacy of that method. Now let me come to the compatibility problem. You see, it all depends, in a sense, on the type of constraints you're adopting. I agree completely with what Ariel has just shown, which in a sense I think is also has been shown by Williams in 1980. And that is to say that if you adopt constraints which simply make the data you've actually observed 100% certain by imposing this delta function or a characteristic function, setting the expectation of a characteristic function equal to 1 in case the data come from a discrete set. In that case, you immediately get back Bayes conditionalization if you maximize entropy, or if you maximize any other expression for that matter, as long as it's a concave function of the ratio of the p's and q's. Unfortunately, it has also been shown by Seidenfeld that this is completely restricted to the case in which your constraint function only takes two values, 0 and 1 for the characteristic function, or 0 and infinity for the delta function. As soon as you allow your constraint function to have more than two values, you can get into a conflict with Bayesian updating. And perhaps for this I can show you a diagram.
Yeah. You want to draw?
Yeah. So let me consider a set of outcomes for which there are only three. Let's call them A, B, and C. And let's consider all the probability distributions over these outcomes. And they can be represented nicely as a simplex in which any point here is a probability distribution, and the probabilities of A, B, and C can be just read off from the baryocentric coordinates of that point. Right? So this is BC, BB, and BA. So this is my space of probability distributions. Now suppose I'm going to impose a constraint in terms of an expectation value, and that will be a linear or affine subset of this simplex, and it will slice up my simplex into a foliation where for each set there's some particular value of the constraint expectation. I can maximize entropy on the subject of these constraints, and for each of these constraint sets I will get some particular solution, and in general they will form a curve which will be the probabilities depending on the particular Lagrange multiplier. Now, knowing that I'm going to impose these constraints from the beginning means that whatever the data are that are going to give you the expectation value, you're going to end up with some maximum entropy solution which falls on this curve. And that curve can have peculiar properties. So for example, in this case, if you look at the probability of B, which is given by this distance, then, and this is, say, the original prior distribution from which you started, you see that whatever evidence you get from the experiment, the probability of B can only decrease because it's always going to be less than the value it had at the beginning. And this violates general Bayesian principles, because if you know beforehand that your posterior probability for a particular outcome is going to be lower than the present prior value you associate with it, then there is a Dutch book that can be made against you and you're not being coherent. And this is particularly troublesome because it will appear no matter what evidence is going to be obtained from the experiment.
Are those expected values?
What are
Those are expected values?
The green lines. The green lines are the collection of all the probability distributions which agree in their expectation value for a certain function. And I let the values of these expectation values change to make this foliation.
So maybe to clarify, that this would, what Ariel was talking about, the family of possibilities. In other words, that was by beta, by the Lagrange multiplier. That's kind of what you're saying. You're right. There's many probabilities based on that expectation value. Is that what you're saying?
Yes, these are all So for a given value of this expectation value, these are all the probability distributions that agree with that expectation value, and this point is going to be the one that has maximum entropy. And as Seinfeld showed, the only case in which this type of phenomenon does not happen is exactly the case when the constraint function only takes two values. And of course, in your reconstruction of Bayesian updating as a maximum entropy method, that's exactly what you do. So yes, in that case, you're completely compatible. Bayesian updating and maximum entropy updating with Kullback-Leibniz entropy is completely compatible. But if you try to do it more generally, then you can run into
the case that I mentioned, in which maybe you don't have a delta function, but you may have a probability distribution, that leads to the Jeffreys rule, which is a special case of Bayesian updating and marginalization. So now I'm not sure.
Well, I'll have to look at that.
Yeah. In fact, well, the reason I asked whether that is an expected value is because it comes back to my previous comments on what you want when you impose expected values in a maximum entropy or entropic inference situation, is that not just impose an expected value blindly because you may want to know it or whatever. You have to impose the the expectation values that actually reflect the information that happens to be relevant to the problem. So without knowing more about this problem and what is the F, I would not claim that this is a legitimate entropic inference.
I know, well, I sympathize with what you're saying, but then the question is, what is actually relevant?
And that's a difficult problem of science.
But
Can you explain again the question of update on this picture? Or the update? Can you explain it again? The question of update. I understand the MaxEnt entropy.
do I have to explain again the picture?
No. The update. What you said about it.
The updating. This is my prior. This is Q. These are the various maximum entropy probability distributions which could figure as posteriors. And depending on which particular constraint I will impose, by the choice of the value of this alpha, I will end up with one of these probability distributions as my posterior. But they all come from this very peculiar one-dimensional set, although I had a two-dimensional manifold of probability distributions available. And since this curve is so peculiar, it always excludes large regions of the probability space.
Why does that bother you?
Why does that bother me? Well,
if
as
I
I
have a
explained,
space
it
and
gets
then
you into conflict with accepted principles for Bayesian updating, like incoherence.
But if I understand what Ariel was saying before, you don't have a point. You do have that line as beta varies. And so you started off with a larger space, and then you constrained it. Well, you expect it to be a one-dimensional space or something, right? So what's the problem?
Well, I told you what the problem is. It leaves you in conflict with coherence, and it allows Dutch books to be made against you.
If I may, I think that I would have to, I may be wrong, but, right? But you may be wrong.
Good at it. Good at it.
Which is a very symmetrical triad. One of the crucial elements in the previous derivation of Bayes' rule from an entropic argument was the fact that one had to choose an appropriate joint space, theta and x. So the fact that you say the prior is a dot there makes me uneasy, because what I would have thought is that the prior ought to be a probability distribution on that whole simplex.
Well,
so maybe that's not it, but maybe I have
well, for ease of argumentation and drawing, I presented this problem in terms of a probability distribution with just three different outcomes, discrete outcomes, so that yes, the class of all probability distributions becomes this nice two-dimensional simplex. Of course, if you have two different continuous classes of outcomes, x's and thetas, then the class of all probability distributions become much larger, and I cannot draw graphs so nicely. But even in that case, I would have a much larger simplex, but every probability distribution, in this case over x and theta, would still be a single point in that space.
Okay, so I think we should end that debate right there. John, do you have anything to say on this?
Yeah, I think so.
Okay.
And I think what I've got to say is on here, actually.
Okay, excellent.
Where is this feeling?
Oh, right.
Oh, sorry, of course. I thought we might get into this. Here's the diagram. So, I've got 6 sides because I put an etc. here. Right. There is a problem about assigning priors and stuff. And different people have different ideas about what a die might be. Mr. A thinks that P is the 6, the 6, the 6, the 6, the 6, the 6. That's where he starts. He knows the die is fair. Mr. B thinks that the labels might matter, because it might be a funny, strange shaped die. And he might put some sort of flat or other distribution in there. Mr. C thinks I is 1 is special, but all the others are the same. So he's got a one-dimensional family. And different people can put down pretty much anything they want in that simplex. Oops. Now, likelihoods come up as to do with moment data, but the general idea of this was that you can forget what the data, the order the data came in, and end up with simply something like a number of spots in 4n tosses. This is the typical constraint. What do you do with it? Well, different priors will have different evidences associated with them, and different posteriors, because all those posteriors can be modulated with the appropriate likelihood. That one won't be modulated at all, because the guy's a religious fanatic and knows it's a 6, the 6, the 6. This guy will end up around the maximum entropy point, because that becomes the maximum likelihood point, because eventually if you crank up enough numbers, then the likelihood is infinitely peaked, and will hit somewhere. If that place where the data get fixed is over here, then of course you'll have to be on this line somewhere and get a different result. But what you get out of this is clearly MaxEnt under the appropriate constraints. And I think that in this is simply a particular case where entropy just happens to be multinomial data, so that if you do take these average positions, entropy is just the same thing as likelihood. So the maximum likelihood, which is where all the probability would be, they're just in the same place. And it's hardly an accident. That's to do with, yeah, now I take the point that if we draw a simplex and take a maximum entropy solution out of constraints like this, then that family of maximum entropy priors won't cover all the space you want. So you get a one-dimensional curve through this six-dimensional simplex. But that's not doing Bayes. Bayesian updating should be equivalent to maximum entropy in this case, I think, is just maximum likelihood. I really don't see it worked, dead failing. The other point is that if we do find a contradiction, then by eliminative induction, since there's only one Bayes theorem, and there's only one information or entropy formula, then we have eliminated the only tools we've got, and we can all go home.
Well, that went perhaps a little fast for me to understand completely, but as far as I understood, Mr. A, B, and C are all doing Bayesian updating on different priors.
Yes.
Yes. So I have no objection against that, but that doesn't tell you anything about compatibility with maximum entropy updating with Kullback like that. And of course, if you take an asymptotic regime in which the number of outcomes go to infinity, then barring some special cases, we all know that all reasonable statistical methods, whether it's Bayes, whether it's maximum likelihood estimation, or what have you, and probably also maximum entropy will all converge to the same answer. That's simply because if the number of data becomes so large, then the questions about what different priors you had or what type of statistical method you used simply becomes irrelevant, because the data speak so loudly for themselves in such large numbers that you would be a fool to get anything different from what they tell you. But I don't think that takes anything away from what I said, in which case I just had with dealing with single observation. But for somebody who decided to do maximum entropy on a particular constraint function, knows beforehand that his posterior distribution will have a quite peculiar shape, regardless of what data he's going to get. And he's not allowed to enter in certain areas of the probability space, in which in case he did follow Bayesian updating, he would be allowed.
It's on.
Well, I think that's right. But that would point to a misapplication of maximum entropy.
Well, what's the misapplication?
Because if I have a 6-dimensional simplex and I put a 1-dimensional constraint on it and put one number, then I must clearly get back a 5-dimensional set of possibilities instead of 6. If the one constraint,
yeah,
that's Bayes. Now, if I take a 6 to 6 to 6 to 6 to 6 as my starting point for the Kullback line, and then select one maximum entropy point, then I'm doing a selection which necessarily gives me 1 point instead of all the possibilities. So necessarily by doing that, I would be cutting off a lot of the dimensionality, and that I think is the point you're making. Now, I don't know exactly what has gone wrong in the symbols, but I suspect that it's your P of x and theta, that you're doing MaxEnt in that particular way.
I don't think
No?
there's anything wrong.
Okay. Well, it's a very strange.
Okay, for time,
Multi-
since we're
Yeah.
super over time.
Let me conclude, because there is an interesting additional point.
Go ahead. One
Okay,
minute.
okay. There is one. If I'm going to claim that Bayesian updating is in any way compatible with entropic updating, there is one basic feature of MaxEnt which is very different from Bayesian updating. Namely, when we update using Bayes, we go from a probability distribution to a probability distribution. When one updates with entropy, it appears that we go to a single point. There is one value there that is privileged over all others. That's not quite what the full method of entropic inference advocates. Done properly, the method of maximum entropy, entropic inference, gives you not just the most preferred probability distribution, but also it gives you a probability distribution around that value, what John initially called quantified maximum entropy. It allows for fluctuations around that value. So that line, that convex line that you wrote, actually may have a width. In such a small simplex, I wouldn't be surprised if what you have is not a single very, very narrow line, but a whole probability distribution over the simplex, so that nothing can be said.
Well, I'm very sympathetic to that idea. I've always thought that, well, maximum entropy, well, singles out this particular unique probability distribution for which the entropy is maximal. And usually there'll be a region around it where the entropy is not maximal, but sufficiently high, and it seems rather well, silly to discard all these
Yes.
probability distributions in favor of the only one for which it's maximum. I wouldn't necessarily do that in terms of a probability distribution, but this type of approach that you use reminds me very much of the likelihood inference developed by Edwards and his colleagues, in which you don't use entropy, you use likelihood, but you don't concentrate on just the maximum likelihood, which gives you the estimate, but you consider the width of that likelihood function, and that actually leads you rather easily to consider the Fisher information on the probability distribution rather than the Shannon entropy.
Okay.
Gives you a metric.
I'm glad we all agree now. And I've gone terribly over time, but I hope you indulge us a little more and are very interested, as I am, to this discussion, because we want to open it up to audience participation as well. I had a third question, which is more just a general tie-in question about opportunities for future research, and I think we've heard of lots of opportunities right here. I also mentioned something about Teddy Seinfeld that Professor Ufing mentioned. He's got a very famous or infamous paper, depending on how you look at it, that's called Why I'm Not a Bayesian. So you might want to look that up too.
I just want to say something about the last issue. I must confess that the question of updating probabilities in a maximum entropy sense, to me, is a little bit obscure, and I do understand the argument of John, right?
Yes.
And I'm wondering, actually I showed this in the presentation, whether the issue of incompatible Bayes rule is due to the lack of consideration of the ergodicity problem.
Of ergodicity?
Ergodicity, yes, because
You mean large numbers?
What
do you mean by ergodicity?
All large numbers, because Bayes rule could become inconsistent, and I do see that using the entropic drivers, and unless there is a constraint on consistency of the posteriors, then the things don't work. They just don't work. They converge to something real strange. So bottom line, what I'm saying is that while you do your updates, you have to constrain that your posteriors remain consistent. That must become a constraint in order
Consistent with what? Or
Consistency means that if your data belongs to one of the three, is one of the three. We have a, well, here we have a continuous space. So if data is generated according to a certain probability distribution, you get asymptotically the right answer. This is
yes, generally you do.
and I suspect, but I'm not a mathematician, so I did not really go into depth into this issue, but I suspect that this is an ergodicity issue.
Well, I also don't understand quite the use of such words economicity here, because in my point of view, that's a physical concept and a little bit extraneous from this probability discussion. But yes, if you go to an asymptotic regime in which you let the number of data go to infinity, typically you will have convergence of all the measures, of all the methods. With the exception, I think, of probably Mr. A that you showed, who had a delta function as his prior. And if you do that, then of course no amount of data will be able to change your mind. And your posterior will also be a delta function. Because if you're sure from the beginning, then no amount of data will be able to shake your conviction. I'm not sure if this answers your question.
No, we'll have to work out the details.
Yeah.
Doesn't calculate this.
shall I answer the last topic, or what is
Sure, if you like, yeah, please do.
well, I'm not actually working on maximum entropy, but if you allow me to make just one comment about its future. Ariel made this remark, quoted James a couple of days ago with his famous quote saying that maximum entropy was a power tool and that you could use it to perform useful work, but you could also cut off your thumb with it, and that it depends on the user what will be the result of using this principle. I actually quite agree with James on this point. But then again, I don't know so much about Canada, but in the USA, it seems that if somebody markets a tool without a proper manual, he will get sued from the users if they find themselves to suffer damage by using the tool in a way which was not probably excluded in the manual. We all know probably the case of the woman who put her dog in the magnetron, the microwave oven, or people who smoked cigarettes and got cancers and sued the tobacco company. Today, manufacturers have gone to the extreme that even if you buy a bag of peanuts nowadays, it will contain the warning may contain traces of nuts. All this is done in order for manufacturers to protect themselves from sues from customers and users of the products. I think that the maximum entropy principle could maybe succeed in the future if people would be able to develop a manual to say how and when and it could be used and how to choose the constraints probably. Because if we all leave it to the judgment of the users as you suggested, then actually I think we're falling back in a situation in which anything goes and it remains an art of the scientist to think of the proper methods, the proper tools, the proper concepts to be used to do physics. And perhaps I agree that's the way physics is done. But then one also, I think, should not pretend that one has a method for how to proceed.
Yes, consistency is important. We're going to have another question. Robert, please, ask your question. I forgot about it.
It wasn't really a question.
Okay, comment.
It relates actually to the first topic rather than the second. I guess I'm not really, my take on this is I'm not really concerned with data analysis, so I won't try and comment on that or get into this sort of entangled arguments of Bayes versus MaxEnt. But I do want to try and occupy one corner of this, which was picked up a little bit by Ariel in his comments, is that I see MaxEnt as an algebraic method. It's not a data analysis method, or rather I don't want to use it as a data analysis method. I see it as an algebraic method of applying constraints which are physical constraints, and by that I mean conservation of energy, conservation of mass, conservation of momentum, these things. And I'm happy for other people to do what they want. I'm not too concerned amongst consenting data analyzers. You can go and do what you want. But I think we're on very solid ground when we look for some of these conservation rules. And so the expectation really reflects, I see it as, it's not so much the fact that it's an average as the fact that it's a total. So you've got a total energy content in the system or some such. And so I think in terms of the future of MaxEnt, if I were to jump into the third topic, where we look for things, and this is the success of thermodynamics as well, where we analyse systems with this method, applying this type of constraint, I think that will be a success. Data analysis, I don't want to talk about. Thank you.
Very good. Any more questions for the panel? Yes.
I think I have something to say about the first one again. I think that there is a great misunderstanding of what the purpose of updating knowledge is and how the constraints are used. And I think that sample averages have nothing to do with that problem at all. And that's probably the reason why James used averages. And the point is that expectation values are called that precisely because if you have a knowledge of a probability distribution and you want to predict what the result of one trial is, it is the expectation value. And in real life, you don't have a sample of n results. Your information is just one measurement. It's not sample of n results. Because if it were, what would prevent you to calculate also the sample variance and the sample skew and all other moments that you can calculate and put them as a constraint again? This is not the point of this exercise. The point of this exercise is you may have used sample averages to form your prior knowledge. But then you make a measurement that produces one number, and you update your knowledge to the distribution that would have allowed you to predict the result using probability theory. I think this is the point of the updating rule. It's based not on number of measurements, it's based on one number that you obtain as an information, and you adjust your knowledge such that you would be able to predict it before you measure it. That's basically the idea. So I don't see any problem with mismatch between sample averages and expectation values because just sample averages have nothing to do with that.
We agree then?
Yes.
We agree?
Maybe I should ask for comments, and maybe I'll get some questions. Anybody have any questions for the panel?
To me, the expect value issue is
talking to the microphone.
Sounds semantic. I would expect opposite as expectation suggests. If you tell me this average or mean, whatever, I would never expect to see it in experiment. So the meaning of that to me is just the opposite.
Yes.
Yes. Good. I think that Adom has failed. We have not produced a food fight for the cameras.
Well, let's see if I can stir the pot.
Oh, yes.
I wanted to follow up on a comment, I think it was on one of Ariel's slides, where he said either use the thermometer or Bayes to determine, I guess I'll call it the Lagrange multiplier of interest. Say. All right, so a couple years ago I went to the National High Magnetic Field Lab, which is all about thermometry and how one measures temperature. And the clear take-home lesson from that meeting was the man with one thermometer knows the temperature. So again, if you are going to use any experimental determination of the temperature, you know, whose thermometer are you going to believe? So I would be very grateful, and this isn't meant to be a slam in any way, I'd be very grateful for any guidance that anyone could suggest for how to use a thermometer.
Okay. I think I can reply to that in the following sense. I said either use a thermometer or use Bayesian inference, which is a way more sophisticated way to do it. In fact, using a thermometer is, I shouldn't say use a thermometer or Bayesian inference. Good thermometry is Bayesian inference because the piece of equipment had to be calibrated in various ways and everything. So it was just a quick and dirty way of saying, just pick a number, use a thermometer, or do it right. In fact, if you want a good result, you have to do it right. Yeah, but I tend to agree with you. Yeah.
I think from the talks and from the discussion, I think you can come away with two things, two categories here, and that is one is about foundational issues. You know, why should you do this? Why should you do that? And the other one is about use. You know, what's useful. For instance, it may be foundationally correct and consistent to do one thing, but highly useful computationally or otherwise to use a cheat, to do something illegal, but to be able to eat because you were able to perform that illegal act. So no, I think in all seriousness, to me that's a very, very interesting dichotomy and very interesting area for future research is to see, okay, you have some consistency argument, you have some foundational argument, now you need to do something useful that you might not be able to use the full method for currently. And so how do you measure this? How do you judge this besides whether you get the food or you don't get the food? Is there a better quantitative way to measure this? Question?
I'd like to know I asked already the question for Ariel. Who will decide when the method is true or not? So please, what is your opinion?
We actually have an answer. Yes, we have an answer. The other day over dinner, we were talking about the possibility of having an ideally rational agent. And we decided that it had to be someone who works in something like the National Bureau of Standards, or NIST, or even better, in the German equivalent, right, in Braunschweig. And so we decided that Marcel Reginato qualifies as being the ideal rational agent. So from now on, we will encase him in a cylinder of glass with appropriate temperature controls. And when anyone wants to know whether something is true or not, or whether it's useful or not, we just direct the question to the standard. That's right. And proceed from there.
Can I pick up on that one as well? Because you're taking this point about being illegal as well. This is very much the same thing. I just want to go back to this slide I had of because I'm sure what we ought to do is always to do the top. Because we always, for professional use, want error bars and everything. We should propagate our uncertainties and not cut them off. Whenever you do cut your uncertainties off, you're kidding yourself, you're doing something illegal. Whenever you make a selection, you're reducing the space of possibilities. But that is not how we proceed as scientists. We want to get understanding, we want simplicity, and to do that, we have no choice but to build simple models, and that involves making a selection. And the best we can do for selection is to use the best tools we have, the ones that are most consistent, the ones that don't disobey elementary symmetries, and the only tool that does that is maximum entropy. That's a selection method, and you're, by not quite doing the Bayesian thing, by taking one answer, 1 point in this simplex rather than 5 dimensions, whatever, you are making a mistake, but it is essential for understanding and for all our technology and power and predictability and so on, that we do this. So we must be illegal. It's the law.
I think I want to go back to something Ariel said when he talked about ethics. This is like ethics. I don't know about anybody in here, but I don't think I can live a 100% perfectly ethical life. I think it's rather difficult to do. It gets back to an ancient Greek argument, right? So it's kind of along those lines again. Ethics.
Oh, but Ira can.
About 20 past 5, which was 19 minutes ago, Ariel, you said something about the nice thing about entropic priors that leads you to not considering a single point that's picked out by maximum entropy, but a close related family, and some of those close distributions have almost the same entropy as the maximum. And what that immediately reminded me of was the entropy concentration theorem, which I have to say, is one of the most stunning things I've ever read. And I'm starting to tell everybody here that I wasted what I thought was a rather nice exercise in looking at the entropy concentration theorem. I actually bought my own casino quality dice. They're quite expensive, from America, and I filed off the corner of one and I filed off the edge of another, and I tried to roll them lots of times. It's unimaginably tedious to roll them 20,000 times. I've got nowhere near that, but with my wife's help I rolled them quite a few times. And then, of course, totally mathematical. I wasted all this at a Mathematica conference when I should have brought it to a MaxEnt conference. So I'll have to do it again and pretend I've never done it before and show you next year. And I'm pleased to be able to tell you the limits of the sampling I did, what James did with the Wolf dice data works absolutely gorgeously, beautifully. My question is, do the panelists think that what James was doing, using the particular sort of constraints that he built up by looking at the disparities in particular over and under counts relative to 1/6 of the 20,000 total, and constructing the constraint function, then maximising entropy again and again, getting the whole concentration, the whole F distribution of entropies. Do we like what he did? Do we agree with what he did? Because he made this simply amazing inference about what this dice, the defects the dice might have had. Maybe someone here, sorry, I've got one more thing. I've never actually read that Jones or any of his trusted agent ever got hold of that registered dice and confirmed that it had the short 3/4 axis or whatever it was, and the chip on the 2-3-5 corner. I'd love to know that that's true. I looked and I haven't sort of found that. That's why I made my own Wolf dice and filed off the edges, etc.
I think that what James did was what good experimental physicists do when they're modeling a system. They make hypotheses, they see how they work, and try to model them. And there is no logical way to make these as deductions. You sort of have to make wild guesses as to how the effects could be actually modeled, described, and see if that sort of works. So from that perspective, I think he was behaving as an ideal scientist.
I support that.
But the nature of the constraints that he used, I mean, whether
they seem reasonable enough, and they were successful to the extent that they actually did describe the phenomenon that was being studied. So I think that it is legitimate.
But it would be nice if his inferences could be confirmed by looking at the actual case.
That would be nice. So if I may finish with the last third question.
Sure, yes, please. That's the last question. This will be our
of course, my own personal prejudice, otherwise I would not be here, is that the future of entropic methods is absolutely brilliant. That does not mean that the use of the method of maximum entropy, MaxEnt, vintage 1950s, is going to remain undisturbed. Of course, we learn to use it, we eliminate the wrong ways to do it, we keep the right ways to use it, and proceed from there. And entropic methods with relative entropy and other criteria, I think are going to be totally successful. We I think already see that the success of some of these methods is being pushed in directions that might not have been envisaged already in the beginning. We have, for example, Robert here talking about the maximum entropy production principle. I think that is a brilliant new direction to go. And of course, being a new direction, there is room for making all possible mistakes. That's the way science works. But unless you try it, you won't know. Another way to go about doing this, another direction, is to realize that probabilities do not just appear in statistical mechanics, they also appear in quantum mechanics. So my own personal favorite for a nice new direction to push these things is in the reconstruction of quantum mechanics, trying to do for quantum mechanics what James did for statistical mechanics. And this is all work in progress. I believe it is fairly advanced progress, and things are working. Again, there is no guarantee that a couple of years from now I'm not going to find out that everything is misguided, wrong, or whatever, but so far it's looking good. So if we have a generic calculus here that allows us to tackle problems like statistical mechanics or irreversible statistical mechanics or quantum mechanics, I think that that is very, very useful. And please notice that when we say that MaxEnt, or more general entropic methods, explains statistical mechanics, we're not tackling one academic problem that a couple of professors in the darkness of their office are happy to tackle. Statistical mechanics is fully like 90% of physics, 70% of chemistry. It's becoming like half of biology. If we can also do quantum mechanics and irreversible thermodynamics, that's a good chunk of science. It's not a little example. It's amazing that just knowing a few constraints can actually give us so much. So I agree with Robert over there.
Final word.
Yeah, I mean, and it's not just physics. I'm finding that information entropy is a central facet of algorithm design for exploring big spaces. There's all sorts of applications coming along.
Well, I have little to add to that, except that I also agree with Robert, but I actually understand what he said to be somewhat different than I would actually see. Look, entropy has been introduced in physics by actually by Clausius, but in statistical physics by Boltzmann. And when he tried to maximize the entropy using particular constraints, he thought of the distribution he was calculating the entropy of as an actual frequency distribution of number of particles who had certain velocities and certain positions. And the energy he was constraining was indeed the total energy of the entire system, because that was conserved, and because he happened to be considering an ideal gas, that total energy happened to be the sum of all the energies of the components. And then he found, of course, the famous Maxwellian distribution. So this had nothing to do with probability theory. It had nothing to do with information theory. It had everything to do with physics and particular assumptions about conserved quantities and about the interactions between the composites of the physical system. And I have no objection against these derivations in that context and in using constraints in that form, because as we said, and energy has a particular physical meaning and physical relevance. It's a conserved quantity, and if it's an additive function, then yes, total energy is just the sum of the energies of the components. That must be constrained in that case. So in that physical context, the choice of the constraint functions is not arbitrary, but dictated by the physics. So if you want to go into that direction more generally and talk about entropy production and so on, the progress you're making is actually by going away from information theory and back into physics. So it's more like a de-Janesification of the maximum entropy.
That'll be the last word. I hope that my hope was that this would capture the spirit of the original conference and carry on through the future as well in terms of the workshop, discussion, future directions. And I think that did it. So let's thank the panelists, please. Thank the audience for indulging me, especially, and the panelists as well for staying way past the scheduled time.